We all know the company Trumpf from its metal cutting machines and its lasers. But the company really became famous, at least in the Netherlands, when it started to develop the drive laser for ASML's EUV source. This could only happen when both companies carefully aligned their working methods. Both had to adapt their engineering culture. More precisely, Trumpf had to adapt to the ASML way of working. I especially wanted to know more about this cultural change. Both Jonathan Müller and Matthias Wissert were willing to sit down with me to tell me more about their experiences in this journey. I'll start with Jonathan, who is responsible for functional architecture at Trumpf. In the next 20 minutes he will tell us more about the technology behind the EUV drive laser. In the next episodes I will dive with Jonathan and with Matthias into cultural aspects and in system engineering. Jonathan, welcome at Bits&Chips.
Yeah, thanks very much.
And thank you for having me at Trumpf here in Stuttgart, or actually Ditzingen. We planned to split our interview in two parts. First we will talk about the technology, and afterwards we take a half an hour to talk about system engineering.
Yeah.
And so Trumpf makes the laser that powers the EUV source of the ASML machines. And Trumpf, of course, has this very famous video with all those lasers shooting around. Yeah. And I actually was wondering what is real and what is artist's impression. Yeah. Maybe you can explain me, looking at the video, what is actually happening technologically.
Yeah, let's do so. You see, that's like standard clean room, so it's, I think, even not specifically Trumpf what you see here. So we do not produce wafers, we produce lasers, so that's what you now see here. And that is really photorealistic, what the machine looks like. Yeah, we don't have such a clock on the machine, but it's kind of, yeah.
That's an insert.
And now we look inside, and basically here, all the hardware that you see is from cut files. But well, first of all, you don't see laser light, right? So it's 10 micron light, but even green light you wouldn't see unless it hits something and gets reflected to your eye. And then there's some hardware missing, obviously, because everything is in housing normally. So it's not as open in the machine as it looks here, but all the hardware that is there is real hardware.
Mm-hmm. And the light is actually 10 micron.
Yes, 10 microns, so that means it's not visible to the bare eye, it's infrared light. Mm-hmm. Yes, and essentially you will feel it because it gets warm or hot. You can get burned essentially but you will not see it. Mm-hmm. Yeah. And now tin droplet, of course, it's much smaller in reality, so you will not see it. And then also, I mean, here you always see the laser beam as a like package type of thing. That what you see now, that is of course artist's impression, because you will not see a laser pulse. And also, it's much longer in reality, so it's a few meters long. While what you see here would be millimeters. So the pulse duration that we have is a couple of nanoseconds, and that is meters and not centimeters in size. So, but hardware-wise, it's photorealistic of real hardware that we have in the system. Yeah.
Now the viewer has to follow all these steps, and actually. Non-technical people for sure wouldn't know what was going on. It's looking great, but what is actually happening from the first generation of the CO2? It's a CO2 laser.
Yes.
What is happening from the first generation to the hitting of the tin droplet?
Yeah. So actually, the machine that we are building is not a laser in the strict sense of a physicist, because it's not a resonator, so the beam is not bouncing back and forth as you would normally have it within a laser cavity, but it's an amplifier, or amplifier chain to be precise. That means we have a seed laser where the laser pulse is initiated. That one is a laser actually. Mm-hmm. And then the beam goes in a linear way through first a pre-amplifier stage, and then through 4 main amplifiers. Mm-hmm. So that's the big cubes you also see on some of the photographs, I think.
The first stage is is an amplification.
Yes. Well, actually, the seed module is composed of lot of stages that all do different optical things. Most are about isolation that I will come to later, but the first thing is that from the seed laser you get a certain pulse that has a certain shape, so both spatially, so beam shape and so on, and also certain pulse lengths, and that is then prepared in the way you want it for the EUV process. That means you cut it somewhat shorter to have the pulse more defined. Using some modulation, so it's like a mechanical shutter, but in fact it's not mechanical. And then there's various stages of pulse shaping and also isolation mechanisms. Because the thing is, we need that amplifier chain because we need pulses on demand. So the droplets come with some jitter at roughly 50 kilohertz, but it's not exactly 50 kilohertz. Because that's the way droplets are generated. So you want, basically the droplet generator pushes a button on the laser and then the pulse is generated.
So there's a droplet generated, but the timing of the tin droplet, actually you cannot control very precisely. So you have to depend on the velocity and the timing of the tin droplet.
Yes.
And so how do you measure the timing?
That is actually something that not Trumpf is doing. That is done by ASML. So ASML develops the whole source, including droplet generator and then in timing. But you still use some optical sensing methods.
Yeah. So then the laser gets a signal that the droplet is released. And then what happens?
And then we will trigger a laser pulse from the seed laser. That is a Q-switched CO2 laser. And then that pulse travels all the way through the amplifier chain. First you have the more interesting stages optically. So we have acousto-optical modulators and electro-optical modulators for temporal pulse shaping. We have polarization controls, we have a delay line, we have the preamplifier. That's all combined on the seed module. The actual seed laser delivers a pulse at, let's say, 1 watt power level, so optical power. And out of that seed module you get like 100 watts. But then in a different geometrical shape, polarization.
Yeah, so it's 100 times
amplified already within that seed module.
Yeah.
And that is also much of what you actually see in the video is hardware on that seed module, because that's like the more interesting stuff. And optically, and then basically the beam just goes through the 4 amplifiers where it's just always only reflected. There's not much more that goes on at this stage. Because then in the amplifiers it's amplified from 100 watts to 30 kilowatts roughly, and for those optical power levels the choice of optical components that you can actually use is pretty limited. So lenses will not work anymore properly because they are not stable at those high powers for CO2. There's no good lens material, so it's basically mirrors that you can use. Of course you can use curved mirrors, but yeah. That is essentially the options that you have then for like beam shaping. So that is mostly mirrors, but you have the high power amplification then going from 100 watt to 30 kilowatt optical power level.
Yeah, and 30 kilowatt, that's the current power.
Current power of the current system generation.
Yeah, and are special mirrors needed for the reflection of those lasers, or is it the normal CO2 mirrors? Well,
normal CO2 mirrors, but of course you need to take care of, you want high reflectivity coatings, and then you need substrates which are stable also at high power levels. Mm-hmm. So you need substrates where you can get rid of the heat that is basically deposited by the laser beam. So in the parasitic heat that you will always get, because your coating is like 99 point something % reflective, but then there's 0 point something % that still end up on the mirror, and those you need to get rid of without disturbing the laser beam. So. And that is something, so if you have a 30 kilowatts beam, then 0 point something % still means that you have to get rid of, let's say, a few hundred watts power levels. So there's different technologies then, either using like direct cooled copper mirrors or like high thermally conductive substrates such as silicon, but there's also other materials being used.
Now, we just visited your test facility, and when we looked at the mock-ups and the systems, they're quite actually enormous. If you only need to hit very small tin droplets, and they are enormous machines, and a lot of it is in the cooling. Yes. So why is so much cooling needed, and what's actually the generation of the real laser power, and what is what do you have to cool?
Yeah, the tricky thing is, I mean, we target at 30 kilowatts of optical power, but then CO2 lasers are rather poor in efficiency. So that means they have, well, as a laser, maybe something like 5 or 7% efficiency. As a laser amplifier, it's even less. So that then you see that you directly end up at something like almost a megawatt of wall plug power that is actually needed to drive the laser. And out of that megawatt, actually only 30 kilowatts get out as laser power. So all the rest, so let's say 900 something kilowatts, is converted to heat at some point. Yeah. And then the losses are kind of all over the place. You have so CO2 laser is always a laser gas that contains CO2, and that is driven as a laser medium by radio frequency electrical discharge in the end. So you generate the plasma in the laser gas, and that is how you pump the laser gas. And then you have, of course, all kinds of conversion losses to get the electrical power into the laser gas as SRF. And then the biggest loss factor is essentially that from the laser gas you only can extract a certain portion of the energy as laser light, and the rest just is converted to heat in the laser gas, and then you have to do the cooling of the laser gas, which is the biggest technological challenge in CO2 lasers, I would say.
Yeah, and the whole module is actually a big gas pumping system. You pump the CO2 gas around and put it in these heat exchangers and put it back in the laser system again.
Exactly, yes. So that is the whole thing about CO2 lasers. So it's really about, well, first heating the laser gas with RF. That is, of course, well, the obvious portion, but then you also have to cool it down again to get rid of all the heat that is not converted to laser power.
Yeah. Maybe it's good to explain why the choice for the laser was a CO2 laser, because the CO2 laser actually is hardly used anymore in the industry, while maybe in the 90s it was used for cutting and welding. Why is an old-fashioned laser used for such modern high-end systems?
Yeah, and that is a good question, and I think there's different reasons to it. So one reason is that simply at the moment the choice was made for the EUV technology, so tin droplet 13.5 nanometers. CO2 lasers were simply the most powerful lasers that were available on the market at that moment in time. So it was kind of a natural choice back then, but that was kind of in the late 90s, early 2000s somewhere. And then the other thing is that you always need the whole process chain for a certain wavelength. So the 13.5 nanometer EUV wavelengths that is used today, that requires a material that emits these 13.5 nanometers, so the tin. Yeah. You need a pump source, so high power laser that emits sufficient amount of light at the right wavelength so that the tin absorbs efficiently. That is the CO2 laser. And then you need materials for the EUV mirrors, which is also one of the key challenges, or maybe even the key challenge in EUV is about the whole optical column of the EUV light, actually. That's not the Trumpf portion. That is what the colleagues at ZEISS are doing mostly together with ASML. And you need all of those, and they all depend on the wavelengths. So if you decide to go to a different wavelength, I don't know, 6.5 nanometers or so has been discussed, then you have a new material for the droplet, you need another pump source, you need other materials for the mirrors. Yeah. And that is the whole complexity of the game. And that PIC was once made for EUV, the 13.5 nanometers. And that means also that it's not so easy technically to move away from the 10 micrometers CO2 laser. And one could imagine, for example, today there's very efficient laser sources at 1 micron, but 1 micron is not a very good wavelength to drive the tin process. So that's why those are less efficient, and then you need a laser that has even more power than the CO2 laser, so not 30, but then something like 70 kilowatts or so at 1 micron, and at the moment this still balances out in such a way that CO2 is still the most favorable way of generating that pump light. Yeah. And driving the process.
Yeah, and let's say that maybe in the far future or in the near future, 6 nanometer is considered as a new wavelength, or maybe the Chinese are working on it. Who knows? What would companies have to do, or what would engineers have to do to set up such a system? What are the challenges? You mentioned a few.
Well, I think the tricky part is building. So the laser part, of course, is not easy, but I think that we would be able to solve. But the tricky part is actually developing all the optics downwards, so towards the wafer, and then of course also the wafer end is often being neglected. So like photoresists, masks, all those also need materials, need processes that have to be developed, and there's billions of euros that went into the development of today's EUV technologies. And I think the hurdle is really high to invest another billions of euros in a different technology.
You work for 10 years now at Trumpf, so this question might be pre your career at Trumpf. Yeah. But maybe you can tell us something about how Trumpf got into this business.
Yeah, so actually Trumpf got into this business because they were approached by, at the time, Cymer, which is today part of ASML, on a trade fair. Actually, they were like walking around and looking for strong, powerful lasers to drive the EUV sources. So they at the time thought about laser-produced plasma, so actually the thing that we're today doing with tin droplets and so on. And they were just looking for someone to sell them a laser as powerful as possible to drive this. And then they approached Trumpf, and that's how the whole thing got started. And first it was, of course, a small project, just building a dedicated laser for Cymer at the time, adapting it the way they needed to have it. So at the time, but different configuration than the amplifier that I explained before was chosen, but still it was like taking standard lasers from Trumpf and configuring them in a specific way, and that's how the whole thing got started. So first with, I don't know, 1, 2, 3 developers working on the project, and then when I started in roughly 2015. It was really started as a spin-off of Trumpf, with at the time something like 150, 200 employees, and now we are at way beyond 1,000.
You don't only produce for ASML anymore, you also develop laser for other customers?
Well, actually, Trumpf historically started to develop lasers a long time ago, mainly for other customers, right? So we were already building lasers for the 20, 30 years when ASML approached us to help them with, or Cymer at the time, to help them with EUV generation. So we were essentially laser supplier, and they took us into this business. And the 1,500 people or so that we today have in EUV, they only work for ASML and that type of business. Yeah. But of course, Trumpf has something like 17,000 people worldwide, and the majority of those is not working for the EUV generation.
Yeah, and it's now about 1/5 of the revenue that the EUV business generates. Huh?
Yes.
Can you mention or tell about some milestones that you achieved during the EUV history at Trumpf?
Yeah, I think the most, at least the one that made the biggest difference for us was in 2017, when actually we developed a module on the seed module that serves for isolation protection, because that at the time was the biggest problem, that the whole because of back reflections from the droplet and backward amplification, the whole laser was not stable enough to produce EUV at a stable level.
Yeah, what can you explain that?
Yeah, so basically I explained to you before that we have 1 watt from the seed laser and then 30 kilowatts at the end of the amplifier chain.
Yeah.
Now light amplification in principle is a reversible process, so that means it will work in both ways. So if you have light amplification in forward direction, you also have light amplification in backwards direction. We amplify by 4 or 5 orders of magnitude. That means if we have a reflection from the droplet, and that is, let's say, 1 per mil or so of the forward traveling light, then this would also be amplified by the same 4 or 5 orders of magnitude and then hit the seed laser, well, let's say, to keep it simple, at the same 30 kilowatts power level, and that the seed laser will not like. And then basically the whole thing gets shaky and unstable, because each time you hit the droplet very well, you have more back reflected light, and then it gets unstable. So we needed to think of some isolation mechanisms to basically prevent this, that light can travel through the system in the backwards direction. And that module was called SIM, Seed Isolation Module at the time, and that was the key ingredient to enable that. I think it was the day before Christmas in 2017 where San Diego did the proof that they could produce the 125 wafers per hour, which at that moment was considered the economical threshold for EUV to be economics-wise profitable. And then basically the customer started to not only buy pilot machines, but really go into mass production.
Yeah. To my knowledge, that in 2018, TSMC ordered 20 machines, exactly. and Apple wanted, because Apple wanted to approve the process to be able to make iPhones.
Yes, and for us that was basically the moment that we scaled up our production. And that was actually a time where I was already involved. But there were, but that is like the transition from, well, building single lasers all kind of individually configured to a certain degree and so on, to really going into standard production of higher volumes of machines.
This was the first episode of my conversations at Trumpf in Ditzingen. In the next weeks we will follow up with more about system engineering at Trumpf. As said, apart from the conversations with Jonathan, I will also dive into this with Matthias Wissert, who is head of R&D at Trumpf.